Okay, so now we are going to do section 5.2, infinite series. We already talked about what an infinite sequence is. So an infinite sequence is a list of numbers. An infinite series is a sum of those same numbers. So typically the notation is something like a sub 1 plus a sub 2 plus a sub 3 and so on, which we can write with sigma notation, which is the sum from k equals 1 to infinity of a sub k. Sometimes k is used as the counter, sometimes it's n or q or I. That variable doesn't matter so much. Okay, and then a sequence of partial sums, which we typically use the notation capital S sub n, is slowly but surely adding up the terms of the series. So an infinite series, you add them all up. So if I were to slowly add them, just maybe the first one, and then the first two, and then the first three, and then the first four, that is the sequence of partial sums, which would then often be written as S sub 1, comma, S sub 2, because that is a sequence. That's how that would be written. And then in general, if the sequence of partial sums has a limit, and I should be more specific, has a finite value limit, it converges, then we say the infinite series converges. If not, we say the series diverges. So the best way to think about that is the infinite series is equal to the limit of the partial sums. That's what we're going to use a lot. The infinite series is equal to the limit of the sequence of partial sums. Okay, and then another thing to think about for series is there is more than one way to write the same series. It's good for us to get used to multiple representations for the same thing. So for example, the sum from n equals 1 to infinity of 1/3 to the n. First of all, it is worth our time to just plug in some numbers and see what happens. So if I start off by plugging in n equals 1, I got 1/3 plus, and then if I plug in n equals 2, I have 1/9. And then if I plug in n equals 3, and then n equals 4, etc., etc., etc. Don't forget the dot, dot, dot. And there are pluses here because it's a series, not a sequence. There's more than one way I could have written that. So for example, I also have the sum from n equals 0 to infinity of 1/3 to the n plus 1. Let's see what happens when I plug in numbers to that series. Now I want to start off at 0, but if I start off at 0, that exponent becomes 1. And 1/3 to the 1 is 1/3. Then I would plug in n equals 2 because this is still your counter. But sorry, then I would plug in n equals 1, I'm sorry, because that's my counter. And then 1 plus 1 is 2, and that's where I got the 1/9. And you can see how that would continue on. You should see that those are, in fact, the same exact series. And so a way to think about how to go about doing that is if your index counter went down by 1, then your index in the function has to go up by 1. That is kind of like balancing an equation. So another way to do that, and I'll highlight this one, my index counter was 0, now it's 3. So my index counter, I would say, went up by 3, which means that my index in the function must go down by 3. So that would be going down by 3. And you can see that n plus 1 and then minus 3 turns into an n minus 2. And you can always, and you should always double check. If I plugged in n equals 3 down here, that exponent would become 3 minus 2, which is 1, which would, of course, become 1/3 to the 1. And then I would plug in n equals 4, the next counter, 4 minus 2 is 2, and 3 squared is 9, etc. So multiple ways to write the same series. That manipulation is going to be helpful later on when we are trying to compare series. And maybe we want to change the counter to compare to a completely different series, and yet we want this particular one to stay the same. And you'll see that later on. Okay, so now we have definitions. Let's do some practice. So given the following infinite series, find the first 4 terms of the sequence of partial sums. Then propose a formula for S sub n, which is the sequence of partial sums, and then propose a value for the series. So step one, for the rest of this section, when you're in doubt, just start plugging in numbers and see if you see a pattern. So I'm going to start off, I have the sum from k equals 1 to infinity of 1 over 2 to the k. So I am going to start off by just plugging in some numbers and see if I can see a pattern. If I plugged in 1, I would get 1 over 2 plus, and then I'll plug in 2 and I got 1/4. And then I'll plug in 3 and I got 1/8, etc., etc., etc. Okay, I can kind of see a pattern. I can guess what's happening here, so that's pretty cool. Okay, but I did need to do the next part of the question, and that was find the first 4 terms of the sequence of partial sums. So let's go ahead and find those first 4 terms, which will always be the same. Capital S sub 1 is going to be the first term, whatever is here. That's why you should list out the first few terms of the series and then list out the first few terms of the sequence of partial sums. So S sub 2 is the sum of the first 2 terms. So 1/2 plus 1/4, which feel free to use your calculator if you'd like, but make sure that you leave things as a fraction. It's certainly not required, but in this particular example, I can tell you it's easier to recognize a pattern. S sub 3 would be the sum of the first 3 terms, and I already used my calculator and I added those up, kept that as a fraction. S sub 4, whoa, I'm so sorry. I am so sorry about that. There we go. S sub 4 would be the sum of the first 4 terms, and I already used my calculator, so I will tell you that I got 15 over 16. And then typically the notation that we would then use is S sub n as a sequence. Now we already listed out the terms of the series. Now I'm listing out the terms of the sequence of partial sums, which is what I got when I was slowly but surely adding up the terms. And I can do another one if I were to add up just for fun, use my calculator, add the 5th term as well, and I would have ended up with 31 over 32. The more you do, the easier it's going to be to recognize a pattern, because the next thing I needed to do was find a formula for that sequence of partial sums. So now let's find a formula. So let's recognize what's in common. Well, they certainly are all fractions, and they all have a power of 2 on the bottom. And then you might also notice that their numerator is always 1 smaller than the denominator. So 2 to the n minus 1. And remember, you should always think about what you're starting at. I started counting at 1, not because my series counted at 1, has nothing to do with that, but because my sequence of partial sums started counting at 1, and we should double check that it works. Plug in 1 into the formula that you are proposing and make sure that you get 1/2. If I do, then I'm good. So 2 to the 1 minus 1 is definitely 1 on top, and 2 to the 1 is 2 on bottom. Okay, so we are good. That is my formula. I can circle that because that was the formula for the sequence of partial sums. If you'd like, I can also circle this one because that was the first few terms of the sequence of partial sums. And now let's do the next part of the question, which is propose a value for the series. So the main thing so far is the infinite series is equal to the limit of the sequence of partial sums. And we found a formula for the sequence of partial sums, so I can replace that with its formula. Then I can do my calc 1, calculate this limit. This is an infinity over infinity, so I can do L'Hopital's rule or Bernoulli's rule, same thing. The limit as n goes to infinity, the derivative of the top divided by the derivative of the bottom, and I got 1. So this infinite series converges to 1, which I think kind of makes a little bit of sense. If you were to start adding these numbers up, like 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32 plus 1 over 64, and if I were to do that maybe in my calculator for the first like 700 terms, it's going to be about 1. So it settles down and it converges to the value of 1. Okay, there was a little bit more to that question, so I want to make sure that we answer the whole question. And there was this next part, which I'm going to do as well, which is in parentheses, how would that have changed if I started at 0 instead? So what I'm going to do is kind of off here to the side, this little box right here, I'm going to answer that. What if, and I'm not re-indexing it here, I'm actually asking how it would change. I'm not trying to keep it the same. So I'm not going to do the whole add 1 and then subtract 1 to keep it balanced. I'm actually changing the series to start at 0. When in doubt, start plugging in some numbers and see what happens. If I plugged in 0, I got 1. And then if I plugged in 1, I got 1/2, and then maybe plug in 2, and then 3, etc., etc., etc. Notice that that 1/2 onward is what we just calculated to be equal to 1. So really I have the 1 plus 1, which is 2. So changing the index changes, changing that starting value changes the ending value of the convergent series. They're both convergent, they just added different numbers. Okay, let's do another one. Very similar idea, but maybe a little bit less work. Given the following infinite series, find the first 4 terms of the sequence of partial sums. And then we're not going to find a formula for the sequence of partial sums. We're just going to propose a value for the series. So like we did before, when in doubt, start plugging in some numbers and see what happens. That's always the good starting point. So I will start off, plug in 1, I got 1.5. And then I plug in 2 and I got 2.25. And then I'm going to plug in 3 and then I'm going to plug in 4. Don't forget your dot, 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 because this is an infinite series. Then I will do my sequence of partial sums where S sub 1 is just the first term and S sub 2 is the sum of the first 2 terms, whatever that turns out to be. And then S sub 3 would be the sum of those first 3 terms, which is 7.125. And then S sub 4 would be the sum of those first 4 terms, 12.1875. So then I have my sequence of partial sums is this sequence of me slowly but surely adding the terms together. And that's also infinite. I just only added up the first 4. And no, it didn't ask me to find a formula, so that's nice. I just need to propose a value. What do you think is happening? Really, truly, like, what do you think is happening? I have the sum from k equals 1 to infinity of 1.5 to the k. It needs to be the limit as n goes to infinity of that sequence of partial sums. So what do you think is happening? I mean, I'm just adding bigger and bigger and bigger numbers, right? That's definitely going to shoot off to infinity. So we would say that the series diverges. Ta-da. Okay, so now we have what a series versus a sequence of partial sums is. Great. Now we're going to do a special type of series. We have 2 special types of series in this section. The first one is geometric. So let's do a geometric series. In general, a geometric series looks like the sum from k equals 0 to infinity of ar to the k. Let's plug in some numbers and see what happens. In this case, if I plugged in k equals 0, I got a times r to the 0, but r to the 0 is 1. Plus, and then I would get ar to the 1, and then plus ar squared, plus ar cubed, plus ar to the 4th, and then you can see the pattern to that. Cool. Now I'm going to think about, just like we did before, once I have a first few terms of my infinite series, I am now going to think about the sequence of partial sums. So S sub 1 is just the first term, and the first term of the series in this case was A, and then S sub, I said it. There we go. S sub 2 would be the sum of the first 2 terms, and those are not like terms, so they are there. So S sub 3 would be A plus AR plus AR squared, and then S sub 4 is A plus AR plus AR cubed, AR squared plus AR cubed, etc., etc. I could do S sub 5, which would be the sum of the first 5 terms, and so on. What I want to do now is come up with a formula for S sub n. And I'm going to do that by recognizing a pattern. I noticed that S sub 2 went up to r to the 1. S sub 3 went up to r squared. S sub 4 went up to r cubed. So S sub 5 would go up to r to the 4th. So S sub n would go all the way up to ar to the n minus 1. Just notice that that index was 1 higher than the exponent, so that index was 1 higher than that last exponent. Cool. All right. So now I have a formula for my sequence of partial sums. It might be worth your time to write that down because that really truly is the formula for the sequence of partial sums. Cool. Okay, I'm going to do something with that formula. I'm actually going to do quite a bit with it. I'm going to call that equation number 1 for right now. But what I'm going to do is I'm going to simplify that formula. I am going to multiply both sides of that equation by r. And if I do that, I'm going to keep my equal sign there. I would end up with rs sub n. I'm just multiplying by r, and then I'm going to multiply this guy by r, and then I'm going to multiply each one of those by r, and I would end up with ar plus ar squared plus ar cubed plus ar to the 4th all the way to ar to the n. And I'm going to call that my second equation so far. And now I'm going to take those two equations and I'm going to subtract. So I am going to subtract equation 1 minus equation 2. I'm going to keep my equal sign here so I don't lose it. But I'm going to do the top one minus the bottom one. This guy minus this guy, and then copy it down. And then I have my equal signs I copied down. Now I'm going to do a nice little trick. I'm going to give myself some space. You don't need to rewrite it if you don't want to, but just watch with me. I'm just going to shift it over a little bit. Just so the squared is on top of the squared, the cubed is on top of the cubed. It's easier to do math in my head if I see them one on top of the other. So now I have a minus nothing, which is a. And then I have ar minus ar, which is gone. So those are gone. And then ar squared minus ar squared, which is gone. And then ar cubed minus ar cubed, which is gone. And ar to the 4th minus ar to the 4th, all the way down to ar to the n minus 1 is gone. And it looks like the only one that's left is that minus ar to the n. Cool, and then I'm going to factor and see what happens here. This was on the left side. There is an s sub n in common. On the right side, there is an a in common. And now I have a formula for my sequence of partial sums. This is the simplified version of my formula for the sequence, there we go, of partial sums. Okay, and just like we did for those first few examples, the value of the series is equal to the limit of my sequence of partial sums. So now I'm going to do the sum from k equals 0 to infinity of ar to the k. That was my original series way back at the top of the page, is going to equal the limit as n goes to infinity of my sequence of partial sums. But I now have a simplified version of my sequence of partial sums. Now I'm going to do a little what if game. Okay, what if the absolute value of r was bigger than or equal to 1? Okay, first of all, if r was equal to 1, that formula is useless. Can't divide by 0. But if r is equal to 1, I'm going to scroll back, maybe just watch with me. This is important to watch. If r was equal to 1, then the original series would be a plus a plus a plus a plus a infinitely many times. And a is a number. It might be 2. Like 2 plus 2 plus 2 plus 2 plus 2. Forever, yeah, that's going to diverge. Okay, right. And then also if R was bigger than 1, let's say like 2. If R is 2, then this guy would be a 2 to the power of a really large number. So this would approach infinity divided by 2, right? With some negatives involved in there, and that would simply diverge as well. So then if the R is bigger than or equal to 1, then that limit would go to infinity, or the original series would go to infinity. It quite simply is that series diverges. So what about if the absolute value of R is less than 1? Think about like 1/2. If the absolute value of R is less than 1, then 1/2 to the power of n would really approach 0, just like it did when we did this geometric sequences. So that would approach 0, and then the answer to this limit would become a on 1 minus r. If the absolute value of R is less than 1, then I have converges. Okay, so now we have a summary for geometric series. And here is the theorem that I have typed up, the summary of what we just did for a geometric series. If the absolute value of R is less than 1, then the infinite geometric series converges to A on 1 minus R, where R was the common ratio, just like it was in geometric sequences. And then if the absolute value of R is bigger than or equal to 1, then the series diverges. Something that I think will be really important to note here. A is, what is A? Let's go back. A really, truly, truly, truly is just the first term of the series. It's really worthwhile to remember that because there's so much going on. It's hard to keep track of it. So write this down. A is the first term of the geometric series every time. Cool. Okay, so let's do an example. Part A, the sum from k equals 0 to infinity of 3 to the k. Start off by plugging in numbers. And if I start off by plugging in numbers, maybe I simplify along the way. I got 1 plus 3 plus 9 plus 27 plus 81. Don't forget your ... to denote that this is an infinite series. This is geometric, and I know it's a geometric series because I have a number to the power of k, or n, or q, or j, or whatever your index is. I have 3 to the power of k. So in this case, I know this is geometric, and my r is 3. And my r is 3, which means the absolute value of r is 3. And 3 is bigger than or equal to 1. And if r is bigger than or equal to 1, the series diverges. Again, the sum from k equals 0 to infinity of pi to the k times e to the negative k is equal to the sum from k equals 0 to infinity of pi over e to the k, because that's how negative exponents work. And I could start listing out some terms. I got 1 plus, and then I would get pi squared, pi to the 1, I'm sorry, pi to the 1 over e to the 1, and then plus pi squared over e squared, etc. In this case, what is the r? In this case, my r is the number that's being raised to the power of k. In this case, that's pi over e, which means the absolute value of r is pi over e, which is 3.14 divided by 2.7, which is about bigger than 1. Yeah, okay, so it's bigger than 1, so that means that this series also diverges. Fantastic. Let's go again. What about the sum from k equals 0 to infinity of e over pi to the k? Start plugging in some numbers, and I got 1 plus e over pi plus e squared over pi squared, etc. And in this case, my r, which is the number that's being raised to the power of k, is e over pi. You can type that into your calculator if you'd like, but it is definitely less than 1. And that means it converges. Okay, not only does it converge, so let's write that down. Maybe we should write down the word converges so we don't forget. Not only does it converge, it converges to a on 1 minus r, where A is the first term of the series. It doesn't matter how ugly it is, A is the first term of the series, and then R is the number that's being raised to the power of K. So I ended up with pi over pi minus E converges. Cool. Same thing. The next one, start plugging in some numbers. If I plugged in 0, I got 1. And then I plug in 1. And then I plug in 2. Sorry, 7 squared is 49, etc. My R in this case is 4/7, which means the absolute value of R is 4/7, which is less than 1, which means it converges. Not only does it converges to the value, I'm sorry, I'll try to keep the colors the same. It converges to the value of A on 1 minus R, where A is the first term of the series, and R in this case was 4/7. Type that into your calculator if you'd like, but let's leave that as an exact answer, and I got 7/3. All right, for the next one, you can see that it's geometric. You can also see that R is -1. It's the number that's being raised to the power of K, which means that the absolute value of R is 1, which is bigger than or equal to 1, so therefore the series diverges. Okay, the next one, you can see that it's the sum. Let me get a better coordination here. This is the sum from K equals 0 to infinity of 3 times 4/7 to the K. This is geometric where R is 4/7 and the absolute value of R is 4/7 and the absolute value of R is less than 1. So this converges to A on 1 minus R, where my R is 4/7 and A is the first term of my series. So if I plugged in 0 here, I would end up with 3 times 1, which is 3. All that work for 7. Ta-da. Okay, let's practice a little bit more. Now let's do that same thing, but with decimals. So the exact same thing, but I'm going to do this now with decimals. So write 1.2525252525, or better yet, 1.25 bar, first as a geometric series and then as a fraction. So I'm going to do this one as breaking it up into 2 different pieces. I'm going to look at the pattern first. So 1 is not part of the pattern, so I'm just going to ignore it. I'll come back to the 1. The 1 doesn't matter, it's 1. And then the pattern is that I'm adding 0.25, and then I'm adding 0.0025, and then I'm adding 0.000025, etc. And then, no, again, that 1 is not part of the pattern, so I'm going to ignore it. But the things that do have the pattern all have a 25 in common. And if I factored out a 25, I got 0.01 plus 0.0001 plus 0.000001. Sorry, I was trying to count the decimals there. Plus, etc., which for me, fractions are much more visual. So I'm going to rewrite that as the 1 over 100 plus 1 over 1 with 4 zeros plus 1 with 1, 2, 3, 4, 5, 6 zeros. I was just trying to count the decimals there. Okay, and then this is going to become 1 plus 25 times 1 over 100 plus 1 over 100 squared. I'm sorry, that really was supposed to have 4 zeros. There we go. I just miscounted the decimals. Plus 1 over 100 cubed, and so on. Now you see the geometric pattern. 1 plus 25 times the sum from K equals 1 to infinity of 1 over 100 to the power of K. Cool, and then that's my geometric series, and now I should write that as a fraction. So 1 plus 25. In that geometric series, my R is 1 over 100, which is less than 1, so it converges. So this should be an A on 1 minus R, where my R is 1 over 100, so 1 minus 1 over 100, and A is the first term in the series, which in this case, the first term of that pattern was 1 over 100. And then type that into your calculator to use the math fraction button to get a single fraction. Ta-da! And honestly, it's pretty cool to actually see that 124 divided by 99. So you can see, oh, I really did turn that infinite repeating decimal into a fraction, which I think is also really cool to notice that. You can always check your work that way. Okay, all right, let's do a little bit more of the geometric stuff along the way. So one more time, this is geometric where my r is 1/2, which is less than 1. So this converges to a on 1 minus r, where my r was 1/2, but a is the first term in the series. So if I start off, maybe you do it written down, maybe you do it in your head. In this case, it tells me to plug in k equals 0. If I plugged in k equals 0, this would give me 256. So my first term was 256. So my answer was 512. Same thing for the next one. This one is a little bit trickier, but not too much. My r is -1/5, which means the absolute value of r is 1/5, which is less than 1, so it converges to a on 1 minus r. My r is -1/5. That really will have two negatives there on the denominator. On the numerator, I need to figure out what my a is, and remember, a is the first term of the series. No matter what, for every geometric. And in this case, the first term is plug in 2. So plug in 2. If I plugged in 2 to get my first term was 1/25. So be very careful with making sure you know what your a and r is. Use your calculator to simplify, and I got 1/30. Cool, let's do another slightly trickier one. The sum from k equals 2 to infinity of 3 times -1/7 to the 3k. You can simplify that. I'm going to add another set of parentheses here, and that's going to become the sum from k equals 2 to infinity of 3 times -1/7 cubed to the k. And then you can figure out what that is. -1/7 to the power of 3 is -1/343. So now I have that my r is -1/343, which means the absolute value of r is +1/343, which is less than 1, so it converges, which means this really is equal to a on 1 minus r, where my r is -1/343. Those two negatives will cancel. Your a is the first term of the series. So start off by plugging in k equals 2, and I would end up with 3 times -1/343 squared, whatever that number is after you type it into your calculator to that. All right, that's geometric. Okay, that's the first half of section 5.2. All of this was geometric series. Now we're going to do the other half of this same section, which is telescoping series. This is the other half. So a telescoping series follows a cool pattern. This is not geometric. So there is no a on 1 minus r at all. This is a completely different type of series. We are going to focus a lot on infinite series, and there is a whole bunch of different types of series. This is a not geometric because I don't have a number to the power of k. So just like we did before, let's start off by just plugging in some numbers and see what happens. That's like always going to be step one, right? Let me plug in this case, it tells me to plug in k equals 0 to start. So I'll start off with k equals 0, and I got 1/1 minus 1/2. Cool. Plus, then I'll plug in k equals 1, and I got 1/2 minus 1/3. So this was me plugging in k equals 0, and then this was me plugging in k equals 1. And then plus, now I'm going to plug in k equals 2, and I got 1/3 minus 1/4. That was me plugging in k equals 2, and I could do that all day long. What makes this a telescoping series is some of the terms are canceling. Certainly not all of them, but some are. That's what makes this telescoping. So now that I know that it is telescoping, the next thing I do is find a formula for the nth partial sum. So if I wanted s sub 1, it was 1 minus 1/2. That's s sub 1. And then if I wanted s sub 2, I would add in the second one. And then if I wanted s sub 3, I would add in the third one. So this was plugging in k equals 2 gave me s sub 3. So I'm off by one, one more than I'm off. So S sub 1 would be when I plug in n minus 1, because I'm off by 1 when I start counting at 0. Now this is a finite list of numbers. When you have an infinite list of numbers, you can't do a whole lot with it. You can do some, but you can't do a whole lot. Like I don't know if there's something in common for me to factor out because it's infinity. I can't think of it. Infinity's not a number. But now this is finite. Now I can do stuff with something that's finite. I can do regular math, which is 1/2 minus 1/2 goes away. And of course, 1/3 go away. And then the 1/4 are going to go away. And then everything's going to go away, it looks like in this case, except for the first and last, which is 1 minus 1 over n minus 1 plus 2, which of course you can simplify. And then, just like we did at the very beginning of introducing series in this video, the infinite series is equal to the limits of the sequence of partial sums. Do a little calc 1 and you're going to notice what goes to 0, what doesn't. I ended up with 1. So this is a telescoping series that converges to 1. If you got infinity, then you would call it divergence. If you got does not exist, you would call it divergence. Awesome. All right, so that's the idea of a telescoping series. I'm going to do one more just to help you visualize. There's more than one way to think about these telescoping series. Some of them are going to be easier than others, but we can do it. So I'm going to start off, I'm going to skip a couple. I recommend you do part B all by yourself. Maybe pause the video and work through it. It's not so hard. You can do it. Same thing for part C. For part C, I recommend that you do partial fractions and then do telescoping. That would be the thing that I would do for that one, but I wanted to focus on a couple of the more complicated ones that have the e to the something. So I'm going to do part D. All right, let's do that one together. Step 1, plug in some numbers and see what happens. Okay, that's always step 1. Plug in some numbers and see what happens. If I plugged in n equals 1, I got e to the 1 minus e to the 1/2. Plus, then I plug in n equals 2, and I started at 1 in this case, not a 0, so I'm not off by 1, which is nice. And then I'll plug in n equals 2, and I got e to the 1/2 minus e to the, sorry, I think that's the 1/3, plus, and then I would do e to the 1/3 minus e to the 1/4. This was me plugging in n equals 3, and I would keep going, so don't forget your dot, dot, dot. Now I can notice it's telescoping because some things are canceling. So now I'm going to find the formula for the sequence of partial sums. The trick here is I have to be really careful. I can't call it S sub n because I've already used the letter n, so I do have to just pick up a different letter. So I'll just use m. Why not? You can use any letter you'd like though. So that would be the mth partial sum, which is if I first plug in 1, that's my first one. And then I'm going to plug in 2, and that's my second one. And then all the way until if I plugged in m, that would become my last term. In this case, I wasn't off by 1, which is nice, like I wasn't before. Okay, and then something, now it's finite, so you can start to see that things are going to cancel. That's not so bad. So now I have S sub m is e to the 1 minus e to the 1 over m plus 1. And so then, just like we did before, the infinite series, which is the sum from n equals 1 to infinity of e to the 1 over n minus e to the 1 over n plus 1 is equal to the limits, there it goes, of the sequence of partial sums. This fraction will go to 0. E to the 0 is 1. So the value was e minus 1, converges. Ta-da! All right, so the main part of this video, there's two main things here. We did geometric and telescoping. Those are the two big pieces that you want to focus on. Thank you.